Today we're going to be doing 3.1, 3.2 graphs of reciprocal functions. So this whole chapter is on rational functions, and rational, you recall, means fraction. So we're going to be talking about rational functions. We're going to be solving them, we're going to be graphing them, we're going to be solving rational inequalities in this chapter. Similar to the previous chapter, except we're going to be dealing with rational functions this time. Okay, so by the end of today's lesson, you'll be able to graph rational functions that are really reciprocals of linear and quadratic functions by making connections between the linear and the quadratic functions and the reciprocal. So you already know from grade 11 how to graph the reciprocal of a linear function. We called those last year rational functions. But we are going to get a little more sophisticated this year, and we're going to be able to graph reciprocal functions that have a quadratic on the bottom and not just a linear function on the bottom. Okay, so the rules that we're going to apply today, or the methodology that you're going to learn today, helps you to easily graph both reciprocals of linear functions and of quadratic functions. It's a process. You're just going to have to go through the process. It requires a practice, but it's not difficult at all. And so it's a different way than the way you graphed rational linear functions, reciprocal linear functions last year. Okay, so let's just quickly go over some of these properties. You'll refer back to them, I'm sure, many times. So the properties of reciprocal functions. The intervals of increase on the original function, so the one that you have not taken the reciprocal of, so a linear function or a quadratic function, are the intervals of decrease on the reciprocal function. So we're going to be comparing the original, the linear, and then we're going to be taking the reciprocal. So these are properties of both. If the original function, a linear or quadratic, has a local max, then the reciprocal, its reciprocal, will have a local minimum at the same value. If the original function is linear or quadratic, the reciprocal will have a horizontal asymptote at y equals 0. And you remember what that is, of course. The reciprocal function will always have the same positive negative intervals as the original function. So where it said here the intervals of increase or decrease are different for the original and the reciprocal, it's not the same for the positive and negative intervals. It's the opposite. Okay, at every x-coordinate, the corresponding y-coordinate of the reciprocal function is the reciprocal of the y-coordinate of the original function. Wow, that's a lot, and you'll see what I mean on that one in a minute. The reciprocal function will have an asymptote at each 0 of the original function, and again, we'll see what that means. And if the range of the original function includes 1 and or negative 1, the reciprocal function will intersect the original function at the points where the y-coordinate is 1 or negative 1. And again, you will see that will become clear in a moment. That's not a plane landing, that's my hot tub starting. Okay, and no, I'm not doing this from my hot tub. Okay, so here's an example. F of x equals 2x plus 1. That, of course, is a linear function. That's represented in the red line on the graph below. G of x equals 1 over 2x plus 1. That's the reciprocal, right? Remember, reciprocal, you flip it. 2x plus 1 was, you could really write that as like being over 1. And so when you flip that, you've got 1 over 2x plus 1. That graph, of course, looks like the blue graph that you see there that you are familiar with from grade 11. That was your rational function from grade 11, right? And of course you remember some of the rules about that when you're graphing this. You can think of it in terms of transformations, and you were easily able to graph those. But we're not going to be doing it with transformations. We're going to be doing it a different way in a minute. Okay, here's another example of a quadratic function. Obviously, you can see that this has a vertex at 0, negative 4. It opens up, and if you think about this one being over 1, when you flip it, this is the reciprocal quadratic function. And look at the blue. It's a little bit complicated. It's a fairly complex graph, but we're going to be able to graph that using the properties that we just talked about. All right, let's get started. So first thing it says here is graph f of x equals 1 minus x and its reciprocal g of x. State the domain and range of g of x in interval notation. Okay. On the right here, I've indicated some of the rules, some of the things you have to do, the steps. You're going to use that as your go-to every once in a while when you're doing this. So the first thing you have to be able to do is graph the original function. So I'm going to switch to red here. Oopsie. And I'm going to graph y equals 1 minus x. If you are, if you're a little rusty on your graphing of lines, remember you can always just come up with a few points for a line. It's pretty straightforward. You could do a table of values. You can also put it in y equals mx plus b form and graph the slope and the y-intercept. So I like doing that method wherever possible. So let's just rearrange this. So the slope is -1 and the y-intercept, the b, is 1. So let's start with the b. We're going to graph that. And we're going to apply the slope of -1 over 1, which means we're going down 1 and right 1. Down 1 and right 1. Okay. So I want to draw a nice line, so give me 2 seconds here. I'm going to see if I can get a line program going. Okay, so there's a line. Not bad, and I'm going to now try to make it red. Okay, so you're going to have to know all of your rules for graphing lines and parabolas. So this is where, for some of you who are a little rusty from grade 11 on that, you're going to have to go over that. So I'm just going to extend that. Normally we have arrows on the end. I can certainly put those on. And there's my graph. Oopsie. Okay. So now it says graph f of x. I did that. Identify the zeros. Well, for any one line, there is only one zero. The exception, of course, is horizontal lines, which do not necessarily have a zero. But every other line will have a zero. So I've identified the zero here at +1, and I'm going to draw vertical asymptotes. So let's make our vertical asymptotes green. So I'm going to draw a line again from up here. Let's see, all the way down. I'm going to make that a dotted line if I can. Let me just see. And okay, and then I'm going to make it green. Okay, so oh, that didn't seem to work. Try that again. Properties, line style, negative. I'll make it green. Okay, so I've drawn in an asymptote. So this is part of my reciprocal function. Okay, this is not part of the line. Obviously, a line does not have an asymptote, but what I'm doing is using properties of my original function to graph the reciprocal. Okay, so the first step is wherever there's a zero on the original function, that's going to be part of my reciprocal function, and it's going to be the asymptote. Draw the point on f of x where y equals 1 and or -1. So I'm going to go to on my f of x where y equals 1 or -1, and I'm going to draw in a point there. So I'm going to have a blue graph here. So I go to y equals 1, y equals -1. I see y equals -1. This is a point here on my original at y equals -1, and here. So these are points. These points where the y value equals -1 and where the y value equals 1 are points on both the reciprocal function and the original function. And let's think about why that is. Well, what is the reciprocal of 1? The reciprocal of 1, if we use the reciprocal notation, is 1. And the reciprocal of -1 is -1. So when we have f of x equal to -1, we also have g of x is equal to -1 for that same x value. And if I put that x value in and get 1 for f of x, when I take the reciprocal of 1, it's also 1, and so at that same x value, the reciprocal will be 1 for g of x. So let's just look, maybe we can just look at the specifics of this one. If f of x equals 1 minus x, we know that at x equals 0, f of x is equal to 1, right? Let's look at g of x. The reciprocal function, g of x, is 1 over 1 minus x. Well, when it's g of 0, f of 0 equals 1, g of 0, 0 in there, 1 over 1 is also equal to 1. Okay, so that holds true for this one, and we could repeat that for the -1. There is no other number for which when you take its reciprocal, it's the same number. So those are unique points that are on both the original and the reciprocal, and so we use that property to help us to graph from the original to get the reciprocal. Okay, so let's keep going here. So we've drawn the point on f of x where y equals 1 and or -1, so we saw that. We sketch the graph now of g of x using the asymptotes and the points that we drew. So we understand that we have, when we take the reciprocal of this linear function, that we have one of those rational functions from last year. So we already know what it looks like. We know that there is a horizontal asymptote at y equals 0. We know that there was a vertical asymptote because we drew it in, and I'm just trying at x equals 1. And right now we're going to draw then our graph approaching the asymptotes. There's the one asymptote, the vertical, and it's going to also approach the horizontal eventually. And we're going to go down and we're going to draw the other branch. And so we're going to come up here, approach the horizontal asymptote, approach the vertical asymptote. Okay, so we have now drawn, using a different method, not using transformations, using the original function, we have drawn the reciprocal of 1 minus x. It's talking about labeling. It says label the equation of both functions. So I know the red one is f of x equals 1 minus x. I know the blue one was the reciprocal of that. We called it g of x. And I'm going to say 1 over 1 minus x. That's the reciprocal function. And we've labeled the two asymptotes, and we need to just put the 2 points in that we drew. So we knew that this point is on both. It's the point 0, 1, and this is the point 2, -1. Okay? All right, that's graphing a reciprocal linear function. Can you tell I'm outside listening to the geese flying south for the winter? All right. Okay, it gets a little more complicated now as you remember seeing the graph of the reciprocal quadratic was a little more complex. So again, you need to know how to graph all forms of parabolas. So it can be in standard form, it can be in vertex form, it can be in factor form, and you've got to know how to graph that. So if you're rusty, you need to go back and practice that. Okay, so it says graph this one. I look at this. This is vertex form. I am going to identify the vertex. -1, 4, right? We take the opposite sign of what's in here. I also know that this is a parabola that opens down because of the negative here. So I'm going to go to -1, 4, and I'm going to, oopsie, I'm using red here for my original. So -1, 4. I use my little trick about my a value, and if you don't remember that, if a is equal to -1, what that means is you can go over 1 unit and down your a value. In this case, so over 1, down 1. I'm going to do the same on the other side. Because of symmetry, we can do that. Now I've got 3 points for my parabola. Okay. I also really would like the zeros of this parabola, so I'm going to try and figure that out. And when you can get the zeros by setting this equal to 0. So this would be 0 equals -x plus 1 squared plus 4. Sometimes they don't work out nicely. but I'm going to try this and see if this works out nicely, because I really would like the zeros identified here. Sometimes you can't get a nice value, and you can just estimate as best you can. So we'll get here 4 is equal to x plus 1 all squared. Taking the square root of both sides, we get plus or minus 2 equals x plus 1. So x is equal to negative 1 plus or minus 2. So x is equal to negative 1 plus 2, which is 1. And x equals negative 1 minus 2, which is negative 3. So I've got a point here, and I've got a point here. Okay, so those are important points. Those are the zeros, remember? So I've identified the zeros. I'm going to just draw those asymptotes in right off the bat. I'm just looking for the green. Oh, there it is. Actually, I'm going to do this instead. So I'm going to draw in my asymptote here. I'm going to draw in my asymptote at negative 3. I'll just change those so that they look like asymptotes rather than straight lines. Properties, we'll put in a green color. Probably could have selected that and done that twice, but oops. Okay, so I might as well label them right now. I've got x equals negative 3, and I've got x equals 1. Okay, so I've drawn in the zeros of my new function, or sorry, not the zeros of my new function has asymptotes, vertical asymptotes. Okay, I'm going to draw my original parabola now that I have lots of. I probably should have done that at the beginning, but this is the parabola. Oy, oy. It's very, very difficult to draw with this. So I'm doing the best I can. Okay, so I've drawn my parabola, I've identified the zeros, I've drawn in my asymptotes, and now number 4 says draw the point on f of x where y equals 1 and or negative 1. Remember, that's a point that's on both the original and the reciprocal. So I'm going to go where y equals 1, and I'm going to go to my horrible graph, and it doesn't have to be perfect here, but I'm going to go to where y equals 1 here, and here there's points. I'm also going to go to where y equals negative 1 and see what I've got. I do have a point there on my graph, and it should be outside the asymptote on the other side. So these should be on opposite sides of the asymptote, which indeed they are. You've got to be very careful to make sure that that happens on your graphs. Okay, so I know that these blue points that I've drawn are all points on my new function. Now it says locate the vertex, well there's the vertex there, and determine the corresponding point on g of x. Well, I know, let me just label this point. I knew that this was the point negative 1, 4. And so, for every point on my reciprocal function, I know that I can just put in the same x value, and out will pop the reciprocal of the y. That's the whole idea, right? These functions are reciprocals of each other, and so the y values are going to be reciprocals. So I know that my new point on my reciprocal function is going to have the same x value, but the y value is going to be 1 over 4. It's going to be the reciprocal of 4. So 1 over 4 is 1/4, so I'm just going up a wee bit here, and I know that this is going to be a point on my new reciprocal function. Okay, now it says sketch the graph using the asymptotes and the points you drew. So let's go. We also know here that y equals 0 is an asymptote. That is true of all reciprocal and linear functions. Okay, we're going to have an asymptote here. We're the horizontal one. We're going to have, this is what I call a 3-parter. We have one branch. Sorry, I'm just going to get to the blue here, approaching the asymptote, and this is funky because you can't go past your vertical asymptotes, but I do have to draw a branch in here. I'm going to draw a branch here, approaching my horizontal axis, and again, approaching my vertical asymptote. I'm also going to draw what looks like a parabola with this vertex and the points that I identified that are at y equals 1. Okay, now it says label the equations of both. I've done that. I've labeled the equations of, oh no I haven't, sorry, of both functions, so let's go ahead and do that. The blue one is g of x equals, what was my original function? Negative x plus 1 squared plus 4. So I'm going to just write it as 1 over negative x plus 1 squared plus 4. And the red one is, of course, f of x equals negative x plus 1 squared plus 4. Okay. Got the equations, and I'm going to label the vertical and horizontal asymptotes, which I have done. I have to label the vertex of this. I know what it is. I know it's the same x value, which I should be using blue here. So it's negative 1, but instead of 4, it's 1 over 4, because it's the reciprocal. It's a point on the reciprocal of this function. Okay, and 2 other points on g of x. So I could label this point here, this point here. I could label this point here, this point here. It's up to you which point you want to do, which one you want to label, but I'm going to tell you, I need this point clearly drawn. This will be incredibly important for marks. A lot of you will miss that. A lot of you will just draw a regular old parabola here, and you won't go through at the points where y equals 1. So you're going to lose marks if you don't do that. You don't need to label it, but you need to clearly indicate that point as well. You need to clearly indicate these 2 points at y equals negative 1. So if I wanted to label 2 more points, I could label this point here. I know that this point, sorry, that's not a point on, this point is the point 0, 3, and so this point here is the point 0, 1/3. Oh dear. Let's undo that and that and go there, back here. So this point here is the point 0, 1/3. This point here is the point negative 2, 1/3. So there's another 2 points. Okay, so label 3 points all together. I don't care where they are. Okay. That is example number 1. And that is what, folks, I call a 3-parter. Okay? We had the middle part here that looks kind of like a parabola. It's much flatter, though, here. And we've got 2 branches. And we've got asymptotes. 2 asymptotes this time, vertical ones, and 1 horizontal one. All right, let's do the next example. Example 3 says, graph the reciprocal of x squared plus 0.5. State the domain and range. Oh, you know what? I didn't go back and state the domain and ranges of any of these, did I? Let me just see. Did I ask for it in the very first one? Let's have a quick look at this one. So what is the domain and range of the reciprocal function for the very first one we did? Well, you know that the domain and the range of rational functions is really what it is not allowed to be, right, for domain. So we could say the domain for this one, for the blue one, is everything but positive 1. So you would say it goes from negative infinity to positive 1. Round bracket does not include round bracket, and then from 1 to infinity is good. Okay, that's the domain. The range, well, we can have anything here, but when we get to the x-axis, that's no good, and then it's good from there up. So again, we are just going to start from the bottom, negative infinity. We're going to go to 0. Don't include 0. Then we're going to include the 0 again. Or sorry, we're going to jump over and not include the 0 again. So we're having a round bracket there and back up to infinity. Okay? All right. Next one. The domain and range of the blue function. All right. I think we can do this. Let's make sure. Okay, so let's start with domain. everything's good this way until we get to the asymptote. Then over to here, everything's good until we get to the asymptote. Then we jump over the asymptote, everything's good. So we're really dealing with the asymptotes. So the domain is going to be from negative infinity to negative 3, not including negative 3, and then from negative 3 to 1, and then from 1 to infinity. Okay, so you can just list them, that's fine. Range, let's think about this. We'll start from the bottom, negative infinity, good, until we get to y equals 0, right? So we're going to start at negative infinity and we're going to stop at 0. Can't go to 0. And then can we have a y value between 0 and this y value? Is there blue graph between here and here? No. So our range is going to start at the y value of the vertex. And the question is, do we include that value? And the answer is yes, right? This is the local minimum, and it starts at 1/4. So we are going to include, square bracket, the 1/4 as part of our range. And of course, this blue graph is going to go all the way up to infinity. All right, moving on. Let's follow our instructions again. This is a different example because if we graph f of x, let's see, this is a parabola that opens up, that starts, has a vertex, see, I'll do it in red, a vertex of 0 and 0.5. I know that because if it was written like this, x plus 0 squared plus 0.05, if it looked like that, that would be more like vertex form, so the vertex would be 0 and 0.5. So 0, 0.5 is right here-ish. And I know from my little A trick here that I can go over 1 and up 1. So I'm going to go over 1 and up 1 here, over 1, up 1. Okay. And again, if I really wanted to figure out what my exact value for x was when y is 1, I could, but I'm not encouraging you to necessarily do that. You can just draw your graph as best you can. Hopefully better than that. And I'm okay with you not actually having the perfect point at the y equals 1 and negative 1. Okay, as long as you've just done your best to draw your graph. Okay, so draw the graph of f of x, done. Draw the point on f of x where y equals 1 and or negative 1. So I'll change to blue because I know that's a point on my new function as well. So I go to my original function, I go to where y equals 1, 2 points on my new reciprocal function. At y equals negative 1, you can see that my graph will never be there, so that's insignificant. We don't draw any points there. Okay, if there are no points, take the reciprocal of the y value of the 2 points that are symmetrical to the vertex. So we had points, we were fine, we didn't need to do that. But sometimes you might end up drawing a graph like starting up here, for instance. And if there were no points, then you could just take the reciprocal of a couple of points here and here, the reciprocal of the y's, and you would end up with new points on your graph. So you don't need, this is a trick that you would use when you just don't have any other points, taking the reciprocal. All right, so let's see. Locate the vertex and determine the corresponding point on g of x by taking the reciprocal of the y value of the vertex. All right, so there's the vertex at 0, 1/2. I could probably just draw that in, so 0, 0.5. Or if I say 1/2, does that help? Because when you take the reciprocal of 1/2, you know that that is 2. So the reciprocal is 0, 2. Okay, so now I have 3 points so far. It says, next step 4, draw the graph of g of x using the asymptotes and the points you drew. Well, did we have any zeros? No, so we're not going to have any vertical asymptotes because there were no zeros on our original graph. But we still do always have y equals 0 as a horizontal asymptote. We always have that. So now I've got 3 points, sorry. I'm going to start drawing them, and basically it's going to look like this. Approach, approach. It's not terrible, but it's not great. All right. We're going to label 3 points on our new graph. We're going to draw in the equation. So I'm just going to write in g of x equals 1 over x squared plus 0.5, and f of x equals x squared plus 0.5. Okay, labeling some points here. I know that this was the point, see, 0, 2. And at 1, I'm not sure what that point is, but I could try and figure it out, or I could figure out another point. What about if we just put in x equals 1, and we label this point? When x equals 1, 1 squared plus 0.5 is 1.5. And so the reciprocal of 1.5 is 2/3. I'm just going to show you that. So when I just stuck it into here and then took the reciprocal of it, but I could have stuck it into here. So go to y equals, or x equals 1. 1 squared plus 0.5 is 1.5. 1 over 1.5 is 2/3. I'd rather have it as a fraction rather than decimals, 0.66. So try and work with fractions if you can. This point here is -1. And see, this point, it's not this point, it's this point here, and 2/3. So I haven't bothered to label these points. I didn't want to figure that out. That's okay. I just need 3 points on my new graph. Okay. All right. You didn't have to pick that x equals -1. You could have gone to x equals -2 and figured that out. Just substitute it in again, and then take the reciprocal, or substitute it directly into the reciprocal equation. Whichever. I like to call this particular function a one-parter because there are no zeros, there are no vertical asymptotes. This is just a one, it's only got one part to it, right? It's one graph. Okay, so this is what we call a one-part, and this happens when there are no zeros on your original function. So the previous example, we had a 3-parter, and that occurred, we had 3 parts, right? The blue here, that occurred because there were 2 zeros on our original function. So now we're going to do our third example of a quadratic. It's really our fourth example because we did a linear reciprocal first. But in this particular example, you can see we have f of x equals x minus 2 squared. Well, if I graph that in red, I'm going to end up with a vertex at 2, 0. And again, with my a equals 1, I'll go over 1 and up 1. And this is a different one because it has its vertex on the x-axis, which means that it has 1, 0. All right, so we're going to draw our parabola again as best we can. I'm going to identify the 0 here, and so I'm going to draw that reciprocal, that horizontal asymptote in then right here. Everywhere there's a 0 on the original, there's a vertical asymptote on the reciprocal. Oh dear, I'm just gonna need, there we go. We'll put in the right color. Oopsie, something like that. And okay, I'm going to label this x equals 2. Okay, so I've got a vertical asymptote. I should also label at this point because I know there's always a horizontal asymptote at y equals 0, so I'll label that. And it says draw the point on the function f of x, the red one, where y equals 1 and or -1. Well, you can see that we do have points on the red one where y equals 1. We just don't have them where y equals -1. So if I go here and go to y equals 1, I go across, I've got a point here, and I've got a point here. These are points on my new function as well. And so I've drawn these. Now it says draw the graph of g of x using the asymptotes and the points you drew. So this one, I'm just going to approach my vertical asymptote. I'm going to approach my horizontal asymptote here, and I'm going to do the same thing on the other side. Now these should look fairly symmetrical. Okay, do the best you can. Okay, it says label the equations. So I know that this was the graph of g of x equals 1 over x minus 2 squared. Is that what it was? And this one then, the red one, is going to be just the graph of f of x equals x minus 2 squared. Okay, this is what I call a two-parter because there are two parts only to this graph. Okay, so we've got three unique situations, one where there's a three-parter where there are two zeros on our original parabola. There's one where we have a one-parter where there are no zeros on our original parabola, and of course there's the one where we have 1 0 on our original parabola, and that creates this two-parter. Okay, now we're going to make sure we've got everything labeled. We do need to make sure we've labeled 3 points on our new graph. Actually, in this one I'm going to make an exception, and we're just going to say 2 points because one on each is good enough. So I'll change that to 2 points. And let's see, we've got some nice points here. We can see that when, well, maybe I better double check that. When x is 1, y, 1 minus 2, that's negative 1 squared, is 1. Yeah, so at 1 and 1, I'm going to do that in blue, sorry. 1 and 1, and at 3 and 1, we've got 2 points. I've labeled my equations. I'm good. Got my asymptotes labeled. Perfect. Okay, I do believe that that's the end of the lesson, yes. So we've done a lot today. You're going to need to just practice this. Trust me, it's not that difficult if you just follow the rules. If we go back to some of our properties now, I'll just give you an example of one of them. It said the areas of increase on the original are the areas of decrease on the reciprocal. So let's just look at that quickly. If we are looking at the red graph here and we are going left to right, so we're going this way, we can see that our function is decreasing as we go left to right until it gets to this point, and then it starts increasing. That's the red one. Well, what's happening to the blue one as we move to the right? It is increasing until we get to that same point, right? Until we get to x equals 0, and then it starts decreasing. So the intervals of increase on the original are the intervals of decrease on the reciprocal. That property is holding true. Now the other property that we talked about was the fact that the intervals that are negative on the reciprocal are the same as they're also negative on the original. So if we look at this one, and vice versa for positive. So if we look at this one, the intervals, this one is positive in all of the intervals from negative infinity to infinity, and also the red one is positive from negative infinity to infinity. So let's state the domain and range on this one. I forgot to do that. The domain is, for the blue one, is negative infinity to infinity, right? There's no asymptotes here breaking things up. We're just always continuing here. The range for this particular graph is going to not start at 0, right? It's going to approach 0, so we're going to say the range does not include 0, but it increases then from 0 up until it gets to 2. At that point, it's never going to get higher. This is the local maximum, and we know that we need, again, a square bracket on 2 because it does include this value, this y value of positive 2. If we go back to the very last example, example 4, I forgot to state the domain and range. Sorry, I'm jumping around a lot because I keep forgetting to do the domain and range. But let's just state the domain and range of that blue reciprocal function. You can see that the domain, if we go from left to right and we kind of sweep and we're looking at the blue graph, we can see that there is a vertical asymptote here, and we cannot include that in our domain. So our domain, let me switch to blue. Our domain is going to be negative infinity right up to our vertical asymptote, which is 2. And then we're going to jump over that vertical asymptote. So we're going to start up again after 2 and then continue on to positive infinity. So that's the domain. The range, well, we know that we're never going to hit the x-axis, so we're never going to hit y equals 0. So that's going to be where we start. That's the lowest value. Of course, we don't include the asymptote, so it's a round bracket at 0. And then we can see that it's going to continue upwards onto infinity. So round brackets, 0 to infinity. Okay, so that, I promise you, is the end of this lesson, and you are going to work now on the 3.1, 3.2 graphing activity. You're not going to do the homework in the textbook, just the graphing activity, which is something that you should have printed out. Thank you.